Hello, and welcome to the next installment of the AstroPhot tutorials series. My name is Connor Stone, and today I'm going to take you through learning about group models in AstroPhot. Group models are one of the key features that you're going to need to use if you're going to do anything more than the very, very simplest of fits in AstroPhot. Group models are how you combine multiple models into the same representation of an image. The models or the pieces that you put together can be things like a Sursic model. If there's two galaxies, you're going to need two Sursic models, and the group model is how you combine those together to represent the same image. Similarly, if your sky hasn't been subtracted from your image, you're going to need your model for your galaxy, say your Sursic model, and a sky model added together in order to represent everything that's going on in that image. So let's get started. Just like before, we've got to import everything. Import AstroPhot as AP. That's what we'll be using. And we've got some other things that we'll import along the way. Okay, first up, we're going to need some data to look at. So here we go. This is an image. I'm just showing the data pretty much raw in arctan scale so it doesn't blow out. And here we find ourselves with a whole bunch of little galaxies that are all quite close together. So we realize that the light is going to overlap between some of them, especially these little ones right here. There's going to be some overlap there with the brighter one that they are next to. So this is a case for group models. We're going to need multiple models representing the same image combined together into one bigger model. And that's where the group model comes in. To do this, we're going to need to build up the initialization for our group model. And so you could go by hand, one by one, maybe pull up the fits file in DS9 or something and figure out exactly what pixel coordinates each one of the galaxies covers. So you could go by hand, build out those models like we did in the Getting Started tutorial where we wrote out everything by hand. But that gets really tedious really fast, especially when we've got, what is this, eight little blobs that we've got to represent here. So let's take it a step further in how advanced we are in modeling our images, and we're going to make a segmentation map. So you can use any, it's a Python code, so you can use any segmentation mapper that you want. Here we're going to use the photutils segmentation mapper. It's easy to use, it's fast. There we go. You can look at the way that I've actually set it up here. It's initial segmentation map where I just set a threshold level and how many pixels need to be in the blob in order for it to actually count as something above noise. And then once I've created this initial segmentation, then there's this deblend sources thing, which makes sure that sources that are really close to each other get separated out into different distinct objects. So this segmentation map, in truth, it's just a matrix of pixels with integer values. 0 represents the sky, and then progressively from there, 1, 2, 3, 4, 5, 6, 7, 8. All the pixels that are number 1 should be associated with object 1, which in this case is this little galaxy down in the corner here. Okay, so now we have our data with a bunch of blobs in it. But then at the beginning, we didn't really know anything about, or our program didn't know anything about this data. Now we've got a segmentation map that tells us which pixels are associated with different objects. Okay. Uh, Next thing, let's just load this into an AstroPhot target image. We're going to need that later, so we put it right in there. Note that I've added just a little bit to the sky level for this image. So I've added in a little sky. Originally, it was all subtracted and the data was nice and easy to work with. I've added the sky back in just for demonstration purposes so that we can try and fit that. Okay. Now let's start actually making our group model. We've got our segmentation map, and that has a lot of useful information in it. So we're going to use some of the utilities in AstroPhot to pull that information into a format that we can use. So we use utilities, initialize, windows from segmentation map. So we give it the segmentation map, and we get windows. which is just a dictionary. Here, let's even just print it. Print Windows. This is just a dictionary. And in this dictionary, there's integers that correspond to the integers in the segmentation map. So 1 is the first object. And then you see that there's a list of lists here. So 12, 0, 26, 25. This, these are basically the bounding box edges that AstroPhot is going to use to figure out what pixels are associated with that object, object number 1. And it keeps going through all of the objects that were in the segmentation map. AstroPhot has identified which pixels or what bounding box would minimally enclose all of the pixels associated with each one of these things in the segmentation map. Okay, now those windows that we've got here are the minimum windows that would enclose each segment. But the light from these galaxies is actually going to bleed out further than that. So what we do is we scale the windows. It's another initialization thing, so we ourselves don't need to really care or touch these windows at all. AstroPhot is going to, the utilities in AstroPhot are going to let us just manipulate them the way we want to. So let's expand scale. So we're going to double the size of every window. And we're going to add a border of 10 more pixels around every window. So this is going to make the windows a fair bit larger. And that way, if there's any overlap between the galaxies, we'll be able to represent that in the regions that the windows overlap. Now, in this case, we give it the windows that it's going to have to transform, and we give it the target image that it's going to represent, because we don't want any of the windows to expand beyond the edge of the image. That would be kind of useless to us. So it's going to double the size of the windows, and it's going to expand them by a border of 10 pixels, but it'll stop doing any expansion once it hits the edge of the image. Okay, so that's super useful. The next thing that we're going to want to do, once we've got a window for all of these segments, we're going to want to get some initial parameters inside those windows. Because in a case like this, where there's multiple objects overlapping each other, it can be a little tricky for AstroPhot's automated systems to figure out which galaxy in the window is the one that it should be focusing on. So these initialization tools give it some key basic starting points from which it'll be able to make more robust estimates going forward. Chances are the AstroPhot automated initialization would work fairly well, but this is just more stable if you're going to be doing this on a large scale. So here we get centroids from segmentation map. So here it takes in the segmentation map and the target, and this is going to return for us a dictionary of center positions. So here we go, print centers. Let's run it again. And so here we can see for object 1, here is the centroid. So if you take the segmentation map and you consider the light in the image, so there's the image. If you consider the light in the pixels in the image as mass, then AstroPhot is going to take all the pixels identified in the segmentation map, the brightnesses from the target data, and figure out what the centroid, the center of mass, is for that segment. And that way, we get a pretty decent initial center position for that galaxy inside that segment. We do a similar thing for the position angle and the axis ratio. For this, you need the seg map, the target data, and you give it those centers because a position angle and an axis ratio have to be relative to some position in the image. So we're going to use our initial center for that. So this gives us some really decent, robust starting values for AstroPhot to work with. Next up, because Windows is just a dictionary of keys, where the keys are the number for each object that was found in there, and the values are those windows that we care about, let's go ahead and do a for loop. We make a bunch of models and put them into a Python list. So the name is just going to be the object and then the number associated with that window. We're going to give it the window that we created. We're going to make them all Sursic galaxy models, just keeping it simple for now. We have to give it the target image, of course, because it has to know what it's going to be representing. And the centers, position angles, and axis ratios we collect from that previous cell where we calculated all of these ahead of time. For good measure, let's add a sky model, just a flat sky model into this image, and we should be good to go. Now we have everything we need to create our group model. So, just like making any model in AstroPhot, it comes from the model object, except now the model type is group model. It's a group of models. To make the uh, to make the group model, we need to tell it all of the models that are going to go into it. So we give it a list. Here, the list includes the sky and all of those segment models that we added in before in that previous list. And so it's going to hold all of those. And essentially, any operation that you would have called on a single model, it's now going to pass that operation on to all of the individual models and then add them up together into one combined image so we can use that whole object simultaneously. Then we call the initialize, which, like most of the functions in the group model, it's just going to call initialize on all of those submodels that we've added together. So let's put that together. Boom, it's all initialized. And note, because it's all initialized, the other Sursic parameters, the Sursic index, the effective radius, the brightness at the effective radius, those Sursic parameters have all been automatically figured out by AstroPhot because it had a really solid starting point to work with, that we got those centers, position angles all teed up for it. Okay, so now that we've got this group model, let's take a look at this. Oh, this was just a simple test here. So um, group model has get values. This is just like any other model. You can call get values on any model, and it will give you this 1D vector that has all of the parameters. So it's going to have all the centers, all the position angles, axis ratios, all for all of the models, plus the sky model parameters. It's going to have all of those combined together into one big vector here. And as a nifty little test, I took that vector, repeated it 5 times, so now it's 5 vectors, and I showed how you can VMAP over the group model, call it with the vector of parameters, which in this case all 5 are the same, but they could all be different. And then you extract out the data because it's going to return a model object, a model image object. And so that model image object has an attribute data. And so here we've created 5 versions of the group model image. They're 150 by 150 pixels each. And so this is a vectorized way that you can interact with group models or any other model in a really efficient way, numerically efficient way. Okay, let's take a look at what we've got here. We're going to plot the target image. We're going to plot the windows. So these are those windows that we found and then expanded. And you can see they're kind of all overlapping here, but you'll note that they hit a boundary at the edge of the image. And so this one, especially here, it runs up against that boundary, but AstroPhot handled that for us. And then here you can see the group model. So here, model image, just like when you call model image in the getting started tutorial, we've got our group model that we pass into that function. And the model that it creates is the sum of all the other models. And it looks pretty decent for a starting point. It's clearly not got everything right, but it's off to a good start. So let's try running the bidders. Note that we've got an extra one in here. Instead of Levenberg Marquardt, first we're calling the iter bidder. All the iter bidder does is it goes one by one through each model, and calls Levenberg-Marquardt just on that, but with all the other models still there, like still subtracting from the image, they're just fixed. So it just goes one model at a time in terms of optimization, but it does keep track of all the models because of course they're going to be overlapping with each other. And AstroPhot wants to account for those overlapping models while fitting each one individually. So the iter fitter lets us do that. If you have a group model that can still run Levenberg-Marquardt, that's going to be faster. But sometimes your group models get so big that Levenberg-Marquardt can't fit in your computer memory. And so you can use the iter fitter. There's other cases where sometimes iterating is more stable. We're just going to run it through two iterations of the iter fitter and two iterations of Levenberg-Marquardt. Obviously, you'd want to run it until it says that it's converged under normal circumstances, but this is just for tutorial purposes, and this will get us pretty close, even with just two iterations of each of these. So here we go. It's finished. It took 11 seconds and it did both of them. No problem. Now let's plot that model again and the residuals. And here we go. Now this is looking like a really decent model of that data that we had collected. You'll see in the residuals, it's mostly clean noise residuals, except in the centers of a few of the brighter objects. And that's almost certainly because we have not included a PSF model at this point. At this stage, it's just Sir6 right into the sky. And so we would need some understanding of the PSF in this image in order to get those perfect residuals all the way through. Okay, so now you've uh, collected some data with a bunch of objects in it, created a segmentation map to give you information about all of those objects, used the AstroPhot utilities to get some starting values, created a bunch of models with those starting values that came from the segmentation map utilities, and then created a group model um, that combines all of those little models together. Fitting went very smoothly, and so here we have our fitted group model. Now, group model is an object just like any other object in model object in Python, so you can explore it how you like. For example, let's just print group model, and when we do that, you'll get out all of the information from each of the individual models. So look, here's the models list. So the top level, it's group. That's what I called our group model. Very simple. There's the target image that it's actually representing. And now this list is a list of all the models in the group model. The first one is the sky level. Easy. Second one is object one, object two, and so on, object three, all the way down. And you can see that we've got the parameters for all of them. You'll also note that inside each object is another pointer to that target image. This is not so relevant right now because all of them are pointing to the same target image. But when you get into more advanced AstroPhot fitting, sometimes each of these objects are pointing to different images, and it can get pretty complicated. So all of that data is printed out for you. Okay, they're all pointing to the same target. You can read out all of the values. This is just printing it out. You can also, of course, do group model models. And now let's say object, oops, object 8. Let's say object 8, and we want its axis ratio Q. You call NumPy value to just get the value converted to NumPy off the bat rather than doing it yourself. And if we do this, there you go. That's the axis ratio for object 8. Let's take a look. And sure enough, the axis ratio was 1. It's very circular, this object, and AstroPhot picked up on that. You'll note that it never got exactly to 1, and that's because AstroPhot boundaries are not inclusive of the boundary. So it could never get exactly to 1, but it got really, really close. Close enough for my purposes, at least. Okay. So there you go. In a group model, you can inspect the models, and that's just all of the models in there. It's also, as well as being able to address the objects by name, you can address it as a list as well. So you could do objects, let's see if that's numbered. How are they numbered? They're numbered 1 through 8, but there's the sky level first. So it would probably be number 8. Yes, it is. Number 8. So you can address them as a list as well, and you can just iterate through each one. Uh, that's useful if you just want to do print things your own way. You can iterate through them, print them out how you like. Otherwise, just the default printing format. Okay, so we've made a group model, we've fit it, we've done a good job. But there's some other things that you can do once you've got your group model together. For example, a group model has an extra function called segmentation map. It turns out that once you've got a group model put together, there's a really neat algorithm you can use to create a segmentation map from your group model. All it does is it goes to each pixel and asks which model has placed the largest fraction of its light into that pixel. So the sky model is everywhere, but that has to be spread out over the whole image. So it's only got the total sky flux divided by all the images is in terms of what percentage of its light is going into every pixel. Whereas this model here, there's a certain point out to which it's placing a larger fraction of its total flux into each of those pixels than the sky model. And it gets really interesting when models are close to each other as to which model is placing more of its light in a given pixel. Um, so that ends up giving you a really clean segmentation map for all of your images after using the original segmentation map to get things going. AstroPhot can also do deblending. So you call group models and then deblend. And what it'll do is it'll take your original target image and create a whole bunch of mini target images that are basically just the flux from the original full target image redistributed into each one of the targets. It's best to just see it. So here we go. This is the this is the original full target image where every pixel, 100% of its flux is accounted for across all of the objects, but the flux from each pixel is divided into sub-target images that represent each one of the individual models. This is pretty helpful if you are using a simple model like a Sursic, but then the object itself is more complicated, like say it's got some spiral arms or something, and you're worried that you haven't quite represented it right. You can do this deblending and then compare the flux that you get from your Sursic model and from this assignment of pixels to that model. And you can compare each one of these for the flux, 7.31 plus minus 0.23. And sure enough, in the deblend, if we just grab the total flux from that, 7.37, it's within 1 sigma. That's easy. For all of the models, it's within 1 sigma pretty much, except the sky level. But we played some funny games with the sky level where we just added a constant factor to everything. So it's not exactly clear that they even should be within 1 sigma of each other. Okay, so those are some extra features that we can do with a group model. Once we've fitted that group model to the data, there's more information that we can sort of pull out from it, aside from just printing out the group model and extracting all of the different parameters. I hope that helps you get into some more detailed astrophoto models where you can combine overlapping objects, combine the sky level, or combine multiple models together to represent a single object. For example, if you had a more complicated galaxy that maybe had a break in its light profile, instead of making a really complicated, like re-engineering a new complicated model, you could maybe just fit 2 Sursic models to that one object and um, have them overlap on top of each other. That's entirely valid to do with AstroPhot. So You can represent multiple objects with multiple models. You can represent one object with multiple models. Uh, Go crazy. Do some really neat fitting, and definitely contact me if you run into any issues. With that, I think that's the end of this tutorial, and I'll see you at the next one. Bye.